Hello, welcome back. Today we want to talk about the orbit of the planets and the concept of escape velocity. Specifically, I want to talk about a fascinating historical story. In the beginning, scientists, the greatest thinkers of the day, thought that the orbit of the planets were all perfect circles, because the shape of a circle was thought to be the most perfect shape. But turns out that the orbit of the planets isn't quite a circle, and so all of the observations were different than the calculations. It took a long time for scientists to really figure out what the orbit of the planets were. Now, as we send spacecraft from one planet to another, we send it on what we call an escape trajectory using escape velocity, a speed beyond which it can break the gravitational and get away from the gravitational field of the planet in transit to another planet. But have you ever noticed that all of those interplanetary trajectories are also arcs? It appears that never a spacecraft can travel in a straight line. So in this lesson, I want to talk about all of the different orbits that can exist around a planet are actually what are called conic sections. The early theories of the orbits of the planets date back to ancient times, when astronomers first began observing the motions of celestial objects. One of the earliest theories was the geocentric model proposed by Greek philosopher Ptolemy in the 2nd century AD. According to this model, the Earth was the center of the universe and the planets and stars all revolved around it in circular orbits. However, this theory was challenged by the heliocentric model proposed by Nicolaus Copernicus in the 16th century. According to this model, the Sun was actually at the center of the universe, and the planets revolved around it in perfect circular orbits. Although his theory was more accurate than the geocentric model, it didn't fully explain the observed motions of the planets. It wasn't until the work of the German mathematician Johannes Kepler in the 17th century that a more accurate description of the planetary orbits was developed. Kepler observed that the orbits of the planets were not perfectly circular, but instead were elliptical in shape. He proposed 3 laws of planetary motion that describe the relationships between the planets and the Sun and how their orbits changed over time. However, Kepler's laws did not provide a complete explanation of the planetary orbits. Isaac Newton played a crucial role in determining that the orbits of the planets were actually ellipses. In his universal law of gravitation, Newton showed that every object in the universe is attracted to every other object with a force that's proportional to the product of their masses, but inversely proportional to the square of the distance between them. He applied this law to the motions of the planets and showed mathematically that they actually move in elliptical orbits about the Sun, with the Sun located at one of the foci of the ellipse. Let's say you're staying on the ground, and here you are here, and we'll put a little smiley face on you. There you go. And what you're going to do is you're going to throw some rocks. So here is a rock here you're holding, and you launch it horizontally with some speed v. What is going to happen to this rock? Well, it's going to go horizontally for a while, then the gravity is going to pull it, it's going to hit the ground. And it'll hit the ground, let's call it right there. Now, what if instead I just throw the rock harder or faster? So the arrow I'm going to put on the rock is now going to be even longer. We're going to call it a different V, okay? What's going to happen to this one is it's going to go horizontal and it's going to go farther, but it's still going to hit the ground, only farther away, right? So just by throwing it faster with more velocity, I can delay the impact. Now let's take this thing to its extreme. Here we now have the planet Earth, and there's a very tall mountain, right? And now I'm actually going to stand on the top of the mountain. There's my smiley face. And what I'm going to do is I'm going to, instead of throwing rocks, I'm going to fire bullets horizontally from more powerful guns, right? So here it is. And the first one is going to go very far, but eventually, the Earth is going to pull it down. It's going to impact right here. If I throw it harder or faster, it's going to go a little bit farther around the planet, but eventually still impact. If I throw it even harder, you see what's going to happen. It goes almost all the way around the planet, but still impacts. Now let's change colors. If I throw it at the magical speed, which we actually call the orbital speed, then what ends up happening is it doesn't quite hit the ground. It just comes back to where it starts. This is called an orbit. So you can see what's going on is the gravity is still pulling the thing down the whole time, but you have to throw it fast enough, hard enough, fast enough for gravity to curve it down, but it's going so fast that it actually goes all the way around, right? So what I want to talk to you about is I want to talk to you about something called the escape speed. So V sub E is called the escape speed. Escape speed. And this promise is going to have application in the conic sections here in just a second. It's going to be the escape speed. And what that means is that's the speed that your spaceship needs to get to in order to completely break free of gravity and continue on into the universe without ever coming back. If your velocity is less than the escape speed, then you're never going to leave the planet. You'll just go around and around some sort of shape. But if your speed is greater than the escape speed, you're never coming back, no matter what, because you've escaped. You have enough energy to get away from the gravity of the planet. All right, so to put some concrete numbers on here, for Earth, you might wonder, what is the escape speed of Earth? V sub E, to escape from the gravity of the Earth, you need about 11.2 kilometers per second. Now, when you think about it, that's pretty darn fast. You know, another second goes by, that's another 11.2 kilometers. Another second goes by, another 11.2 kilometers. Bam, 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 every second, another 11 kilometers. That's really, really fast. If you're going less than 11.2 kilometers, you're not leaving the planet. You're just going to come back some sort of way. But if you're going 11.3 kilometers per second, then you will never come back to the planet. You'll just continue on into space, right? Now that's for the Earth. You might imagine that for the Moon, you don't need as much speed to escape the Moon. So the escape speed for the Moon is 2.38 kilometers per second. 2.38 kilometers per second. Right? So that makes sense because the Moon is smaller and there's not as much gravity. Now what about for Jupiter? What is the escape speed for Jupiter? You might guess it's higher. What do you think? It's maybe 15, maybe 20, 25 kilometers per second? No, no, no. Jupiter's much, much bigger than Earth. You need 59.5 kilometers per second to escape the gravitational pull of Jupiter and not come out. It's only almost 60 kilometers every second. Think about that. Another second, another second, another second, another 60 kilometers almost each time. And if you're less than this, you're coming right back to Jupiter. It just may take a long time. Now, if this is the Jupiter, what do you think it's going to take to escape from the sun? If you really launch a spacecraft out and try to get it away from the sun, do you think it's going to be maybe like 80 or 90 kilometers per second, maybe 100, maybe 150 kilometers per second? No, no, no. The sun is much, much, much bigger than even Jupiter. You need 618 kilometers every single second to be able to escape the sun. And the crazy thing about it is we have actually built spacecraft and they are in space right now and they are going faster than this. So they will never ever come back to our solar system. They're just going to escape the neighborhood of the sun, floating in space along a certain direction forever. And so we have built spaceships that have achieved beyond escape velocity. And so you should look those up. But anyway, here's the idea. We have escape speed. Why am I telling you all this stuff? Because the shape of the orbit that you're in is going to be one of these conic sections, and it's going to depend on your speed, right? Now, there's one more thing you need to understand before we can actually draw the picture there. We also have another speed called VC, and this is called the circular orbit speed. This is just the speed required to stay in an orbit. So these are the escape speeds. This is how much speed you need to escape completely. I need to be able to tell you how much speed do you need just to stay in orbit. All right, so for an example, for ISS, the International Space Station, or you can think of the Space Shuttle or any other spacecraft we sent up there, the speed that it's in is roughly, I'm going to put little squigglies here because it's not exact, but it changes a little bit, but it's roughly 7.66 kilometers per second. So you can see right now, if the speed of the space station is 7.6 kilometers per second, that is well below Earth's escape speed, and that's a good thing because the astronauts don't really want to escape Earth. They want to go round and round forever. So the speed is less than the escape speed, so that's why we stay in a circular orbit. If you have a speed less than this, then you're going to spiral down and you're going to eventually hit the ground, right? If you have a speed greater than this, you might get farther and farther away from the planet, but you're not going to escape the planet unless your speed is actually bigger than 11.2 kilometers per second. Now, why am I writing all this stuff? Because it was a triumph of science back in the days of Kepler and Newton to figure out what gravity is. And of course, our ideas on what gravity is has changed since then because now we know it's a curvature of space and time. But still, the idea that this marker coming down is a force of gravity and that force of gravity is the same force that kind of holds the moon in orbit, and the moon is kind of traveling around under the influence of Earth's gravity. It was a really huge leap of knowledge to see that the force of gravity that's holding me to the planet is the same force holding the moon and kind of like keeping it going in a circle as well. And it turns out that the shape of the orbits, the shapes a long time ago were thought to just be circles. People thought they were just circles because a circle is a perfect shape. I mean, when you look at all of these shapes on the board, which one looks the most perfect to you? I mean, my money's on the circle. It looks beautiful. It's just perfectly, it's just beautiful. So, you know, back in the days before science, people thought everything must move in a circle, right? But then it was gradually learned that the planetary orbits really aren't circular. They're kind of close, but they're not really circular. And it turns out that the shape of anything in space orbiting a gravitational field like this is either going to be a circle, it's going to be an ellipse, it's going to be a parabola, or it's going to be a hyperbola. And my goal on the next board is to show you why that's the case or how that is the case. So in order for us to do that, I need to draw the Earth. So this is my best representation of the Earth. It's not a good representation, but that's what it is. So this is the Earth, right? This dot right here. And this Earth has a gravitational field around it. It's invisible. It curves space and time, and so everything falls towards towards Earth, right? Now you have at your disposal a spaceship, and the spaceship, for lack of a better, representation, I'm going to draw it like this. This is a really weird, not so great looking spaceship, but your spaceship is obviously some distance away from Earth. Now, if the spaceship wasn't moving at all, if it was just sitting there and then I just like let it go, of course the spaceship is going to be attracted and pulled in and hit the surface of the planet. So people think, in space there's no gravity. That's not true at all. Gravity extends everywhere around the planet. There's gravity acting on the space station, right? There's gravity acting in the region of space around Mars, around Jupiter, around the sun. There's always gravity. The reason the thing doesn't come down to the planet like this is because it's being pulled down, but it's also moving sideways really, really fast. So if it's moving so fast sideways, then the force is going to curve its path. It's still trying to pull it in, but if it's moving so fast sideways, it's just going to end up curving the path into this thing called an orbit. Right? That's why orbits have this circular shape, but as we're going to see in a second, they're not always circles. They're actually most often not circles. All right? So if you're in a spaceship, and if you just let go, it's going to try to come in like this. But let's say you fire your thrusters because you really don't want to crash into the planet like this. Right? If you just give like a little bit of thrust, just not enough to make it a circular orbit, but just a little bit of thrust, then what you're going to end up with is the shape of this thing is going to look like an ellipse. Now the Earth is actually at what we call one of the foci. You can think of the word focused having a plural called foci. The Earth is at one of the foci, one of the focuses, for lack of a better word, of this ellipse. We're going to talk a lot about focus later on. Don't worry about it right now. But the Earth is situated at the focus of this ellipse. And so if you just send this thing on with a little bit of thrust like this, it's going to end up in an elliptical orbit that's very small compared to everything else. So this is going to be an ellipse. And this happens if your velocity of your rocket is less than the circular speed. Remember, I told you, everything needs a circular speed to stay in orbit. The ISS needs 7.66 kilometers per second just to stay in a circular orbit. But if we fire this rocket with less than that, let's say we fire it with 2 kilometers per second, then it's not going to quite make a circular orbit, but it'll still have an orbit, but it'll look like an ellipse. That's one of the conic sections. Okay, so now let's say we stick a bigger fuel tank on there, and we kick it up a notch, and we actually put more velocity into our ship. Let's say we put enough velocity in it so that it, for Earth anyway, it has a velocity of 7.66 kilometers per second. Then that means in that case, that's not going to be an ellipse anymore. I just told you it's a circular speed, so it's going to go up like this. Let's see, how am I going to do this? Yeah, something like this. And it's going to more or less make a circle. Now this pink thing is not exactly a circle. I'm doing freehand, okay? But you can see right here that this is going to be a circle, right? And this means that the velocity is equal to the circular speed, right? Or the circular velocity. So again, we have a circular orbit speed. This is the number. And so if we have a velocity bigger than this one in the first case, but exactly equal to the circular speed, it forms a different shape called a circle. And that circle is the exact shape that comes about when you give the velocity of your ship, 7.66 in this case, kilometers per second. Now, the really interesting stuff happens with what happens if you kick your speed up beyond this. See, the circular speed was 7.66 kilometers per second, but for Earth, the escape speed is way up here at 11. What happens if you give it something like 10 kilometers a second? So it's got more speed than a circle, but not enough speed to escape. It's right in the intermediate area. What's going to happen then? It's got more speed than a circle, but less speed than it required to escape. Let's say we give our ship even more energy, more speed. So it's going to come up something like this. It's going to make an ellipse that's going to come out even farther, and it's going to come back to the same location. You can see the black curve is an ellipse. It looks very similar to what we drew on the board as an ellipse. So we're going to write down that this is an ellipse. And this is if the velocity is greater than the circular velocity. You read it this way: velocity is greater than the circular velocity, but less than the escape velocity. So the velocity is bigger than the circular speed, but less than the escape speed. Then you see everything is opening up. First it was a small ellipse, then it turned into a circle with more speed, then it turned into this large ellipse with even more speed. And then we said eventually there's a barrier here. Right here, of course, if we go above this speed, we're going to escape and we're never going to come back. We're never going to come back if we give ourselves like 12.5 or 15 kilometers per second. But what happens if I give my ship exactly 11.2 kilometers per second? What's going to happen if I give it exactly equal to the escape velocity? You can imagine giving more and more speed. Let's say I give more speed than the black, then it's going to be a larger ellipse. I give more speed than that one, it's going to get even a larger and a larger and a larger ellipse. Eventually I'm going to get exactly equal to the escape speed. And then the ellipse is going to get so big that it technically does close, but the other end of the ellipse is infinity away. That's what happens when you escape. Right on the edge of having the escape velocity, your ellipse, your orbital ellipse, gets so gigantic that the other side of the thing is across the universe and you never actually come back. Technically you're on an ellipse, but it would take infinity years to come back. The ellipse got bigger and bigger and bigger and bigger and bigger, and that shape is what we draw as a parabola on the board. Notice this parabola kind of looks like half of an ellipse, but it's open-ended and it never ever closes on itself. Right? So that's what's going to happen if you give yourself exactly equal to the escape speed. Okay, so let's kick ourselves up to the point where we have something like that. It's going to look something kind of sort of like this. And then on the other side, it'll look something kind of sort of like this. Technically, this will form a closed loop. Technically, when I say that, is that you give yourself exactly this escape velocity. It'll close up on itself, but like I said, the other end of this ellipse is infinity light years away. It's really never going to close on itself. If you have just a tiny micrometer per second less than the escape speed, then it will close on itself millions of light years away. But when you're exactly at the escape speed, the thing never really closes, and you're on what we call a parabolic trajectory, or what we call just a parabola. Parabola. And that's when the velocity is equal to the escape velocity. Now you might have guessed, if you're in a circle with a certain speed and you give yourself more speed, it turns into an ellipse. And if you give yourself more and more and more speed, the ellipse gets bigger and bigger and bigger. Eventually, if you get to the escape speed, it opens up into this parabolic trajectory. Well, if you give yourself more than the escape speed, in other words, those space probes that we built that are actually going faster than escape speed for the solar system, they're not on a parabola anymore. Those trajectories turn into this one called a hyperbola, or also called a hyperbolic trajectory. It's kind of hard to draw it because basically the thing opens up even more, but essentially it's going to look like this. You can say if you give yourself even more speed, I didn't like the way that started. Even more speed, it kind of opens up. It doesn't even bend over that much. It opens up more like this, something like this. And then on the bottom, you can kind of see it coming down, something like this. So you can imagine this thing going on and on and on forever. So this is when you have a hyperbola. So I'm going to have to kind of draw, I guess down here, hyperbola. Hyperbola is when the velocity is greater than the escape velocity. And this is the master diagram of why I wanted to draw this. This right here, I'm summarizing years and years and years of work by Newton and Kepler and all of those people that figured out what the orbits of the planets were. because they could measure the position of Mars in the sky. They can measure the position of Jupiter in the sky. They can see the sun in the sky. They measured it for years and years and years and years and tried to figure out what the shape of them were. And it was very difficult because everybody thought the shape of these planets were circles. It turns out that all of the planets are actually in elliptical orbits. They have a little more energy in general, a little more energy than is required to just maintain a circular orbit. But they're pretty close to circles. They're elliptical, but they're just stretched a little bit. They're stretched a little bit beyond a circle into elliptical territory. And the sun is at what we call one of the focuses, or one of the foci of that ellipse. Okay? So to bring it home, when we have something like this on the board, what you have is, you have a circle, right? You have a circle at low energy. You give yourself more energy and it turns into an ellipse. Right? And then you give yourself more energy and it turns into a parabola. And then you give yourself more energy, it turns into a hyperbola. For a circle, it goes around and around and around in the same shape over and over again. For ellipse, it also goes around and around, but in an oblong kind of shape. For a parabola, technically, it does technically come around, but it's infinity years, so it really never comes around. So it's exactly on that boundary between ellipse and hyperbola, right at the escape speed. That's what a parabola is. And when you go even faster than that, the thing opens up even more, and so it's a hyperbola. All right, so what is this thing called a conic section anyway? Right? A conic section is basically a class of shapes. And you've heard of all of these shapes before. You've probably played with or seen a lot of these shapes before. I know that you have actually. But it turns out that you can get all of these shapes by playing around with these things called a cone. I know you've seen what a cone is. So I have a couple of props here I made and put together to show you where some of these things come from. So the four conic sections, there's four main shapes. When we're going to talk about where they come from, what the four shapes are, and then stick with me because I'm going to show you one of the most amazing applications of conic sections, which is the orbit of the planets and the asteroids. All of the orbits of everything in space is all a different type of conic section. So stick with me for that. All right, so there's four kinds of conic sections. The first one you know of is called a circle. Then we have one that we've also talked about quite a bit in algebra called a parabola, right? But they all come from this cone that we're going to talk about in just a second. So we have circles, we have parabolas. The other two are ones that we haven't really talked about too much yet. One of them is called the ellipse, but I know that you know what an ellipse looks like. It's kind of like an egg shape. And then we have the final one, which we've talked about briefly, called the hyperbola. So we have circles, we have parabolas, we have ellipses, and we have hyperbolas. Those are the four shapes. Now they are different, they do look different, but they're related to one another. Because the most important feature of all of these shapes, these conic sections, is that we can get all of these shapes by cutting and slicing a cone in different ways. And that's why they're all called conic sections. That's something you don't often learn in algebra, but all of these shapes come from cutting a cone up. So let's talk about the first shape. We're going to talk about a circle. I know we all know what a circle looks like. I mean, we've drawn circles since we were in you know, young kids or whatever, but here we have a cone. How can we get a circle from this cone? If you can imagine taking a saw or a knife and slicing through this cone exactly perpendicular to the base, so you're cutting straight across like this, and if you could kind of separate it and look at it, then the cross section of what you would cut through would be called a circle. And so I've actually done this right here. So here's another one of these cones, and I did this myself, okay, so it's not perfect, but if you slice through this cone exactly kind of perpendicular or parallel with the base, I should say, and take the top off and look at what you get actually is a circle. This is a perfect circular figure. Now, if you had a perfect cone and a perfect knife and you did everything perfectly, this would be a perfect circular shape. You can see the exact same shape on the part that you've cut off as well. So you can see that you can get this beautiful, perfect shape. You know, the ancient Greeks thought circles were the most perfect shape, right? You can get this perfect shape called a circle simply by slicing through a cone in a certain way. Right? And so the shape of a circle you all know is, I'm going to try not to screw it up too bad, looks pretty much something like this. Is that perfect? No, it's not perfect. But the shape of a circle can come from slicing through a cone. Now, the next shape is, for the next type of conic section, beyond a circle, is what we call I kind of do them in different orders, but I like to do the next one because it's mostly closely related to a circle. It's called an ellipse. Now I know that you probably have an idea in your head what an ellipse looks like. It's kind of like an egg shaped. But in math we have more formal definitions. So if you were to take the same cone, instead of slicing through it exactly like this, if you were to pretend this piece of paper is a saw. If I were to slice through it at an angle, in other words, don't slice through it like this straight on. Don't slice through it like this straight on, but tilt it at any angle I want. It doesn't matter what angle, just any angle, just pick it and slice through it like that. And then look at the cross section that's cut away from that. You would see that it would form your typical egg-shaped type of ellipse. All right, so here's my best representation of that. Is this perfect? No. But here's another one of these cones, and you can see that I've cut through it at an angle. Is that angle straight across? No, it's some oblique kind of angle like this. Just I picked a random angle. If you were to take apart the thing and look at it, you would see that this is a perfect oval shape. Is it perfect? No, because I did this by hand and I colored it by hand. But that's the idea. It gives you an oval shape. And if you look at the part that I cut off, it's more or less oval shaped as well. So I'm using the word oval, but the proper mathematical word is called an ellipse. This is a mathematical shape. It's called a ellipse. It's part of the family of what we call conic sections, because we can take a section of a cone and generate that shape that we call an ellipse. So the next conic section that we learn about is called an ellipse. Right? Now this ellipse, you all know more or less what an ellipse looks like, but it comes from slicing a cone in a certain way. Now I'm probably not going to draw a great ellipse, and I apologize for that, but here's my best effort, okay? It's not perfect, it's a little bit too flat. You can kind of see that I flattened it too much, but the bottom line is it's an oval shaped thing. Now, the exact size and shape of the circle, the exact size and shape of the ellipse, all depends on exactly how you cut through the cone. I just picked a random angle. If I pick a different angle, the shape of the ellipse will be slightly different, but it'll have the overall same characteristics. All right, the other thing is that the circle can have different sizes, okay, of course, and the ellipse can have different sizes. It can be really stretched thin, it can be closer and closer to a circle. All of those details come from exactly how you cut the cone, and the equation of a circle is something we're going to learn very soon. The equation of an ellipse, we'll see, it looks very similar to the equation of a circle, and we'll see how it describes each of these shapes. Now, the third conic section is one that we've talked about quite a bit before, because we've learned about parabolas. Remember, parabolas, like y is equal to x squared, that forms that nice smiley face parabolic shape, the parabola shape. It's something we've been learning about for 3 or 4 units now in algebra, called the parabola. It is also one of the conic sections, and it can also be obtained by taking one of these cones and slicing through it. How do you make a parabola from a cone? Well, if you can imagine, instead of slicing it, we're not going to slice it horizontal, we're not going to slice it at just some random angle. What we're going to do is, if you notice, the cone has kind of the sides have a nice angle to it, right? However, whatever your cone looks like, it's going to have some kind of angle. If I cut through it, let me see if I can gesture with my hand. If I cut through it parallel to this side, like if I'm going to kind of mirror this side, I'm going to take my hand and I'm going to cut parallel through the other side of the cone, but parallel to this side. In other words, not just any angle I want. I'm going to match it to this side and cut straight through it. Then what I should get is called a parabola. So it's the very special case when I cut exactly parallel to the other side. So this is my best effort at trying to do that. Okay, so you can see here is my cone, and you can see I have one side down like this, and you can kind of see the cut that I made as best I could. I tried to cut it as parallel as I could straight through like this. So I'm going to separate that for you, and I'm going to show that to you, and you can see that looks like a parabola. In fact, let me go ahead and put this down, and let me turn it upside down, because that's usually how we graph parabolas. We kind of oftentimes graph them upside down, but you all know that parabolas can be the other way as well. So you can see it has that perfect shape. It comes down, it's nice and rounded at the bottom like this, and then it goes back up. This is called a parabola. So it comes from slicing a cone, so it is one of the conic sections. So now we have circles, which are cut by taking a cone and cutting it straight across. We have ellipses, which is slicing a cone at some random angle. And then we have parabolas, which comes from slicing it through at an exact angle parallel to the other side of the cone. And then we have the fourth conic section, which is called a hyperbola. This is one we haven't talked about very much at all. And of course, there's an equation of a circle and an equation of an ellipse, and there's a different equation for parabolas, which we've actually looked at a lot. And then we'll be talking about hyperbolas, which will have a special equation for them as well. So a hyperbola is probably the hardest one to describe, so I'll do my best. You have to envision two cones, one on top of the other like this. And if you do that, it kind of makes sense because, let me kind of do it like this, I guess. If you imagine two cones, each of these shapes so far, in fact, I kind of forgot to write parabola down. Let me take a second to do that. So let's write parabola. I apologize for that. We've done parabola so much, I kind of forgot to write it down. So the parabola is this nice rounded bottom shape that kind of goes up like this. That's what a parabola is. But notice that we cut the cone in one location, we got one shape. We cut in a different place, we got one thing called an ellipse. We cut it parallel to the other side, we got one shape called a parabola. But if you really think about it, all of the shapes that we have done so far, really, it's easier to visualize them if you visualize the cones one on top of another like this, all right? So if we take the top cone and just cut it in one location, we get one circle, only one shape. If we take the top cone and cut it at some random angle, we get one shape. It's called an ellipse. If we take the top cone and we cut it exactly parallel to the other side, we again only get one shape. It's called a parabola. But now we're going to take these two cones as a pair. And we're going to cut them, but instead we're not going to cut them at a random angle and we're not going to cut them parallel to the side. We're going to cut them straight up and down. So if you can imagine this piece of paper is a saw, I'm going to slice through the top straight up and down, and of course then I have to slice through the bottom one as well. So this shape, because it's actually two cones kind of stacked on top of each other, it slices through two different cones. So a hyperbola actually has kind of like two curves. They kind of come in pairs. So the parabola is only like one curve that's generated. You can see how we did that a minute ago. The ellipse and the circle only generate one curve when we slice through. But because we're slicing through two cones straight up and down, a hyperbola kind of comes in two halves, two oppositely oriented curves. And they look kind of like parabolas, but they're not the same thing as a parabola. So let me show you what happens whenever we take a cone and we try to slice it in that way to form a hyperbola. So again, you have to envision there's two of these, one on top of another. I only cut one of them. So you take this guy and you slice it not at a random angle, but straight up and down. Straight, it's not parallel to this, not parallel to this, straight up and down. And you separate that, and this is what you get. You get something that goes up, it's rounded, and it kind of comes back down like this. Now again, if I had another cone on top of this, like this, and I sliced through the bottom one, and then I also sliced through the top one, I would have another kind of cousin curve kind of coming from the top cone here. I just didn't actually slice through two of them for the demo here. But the point is hyperbolas come in pairs. So if I'm going to write that down for you, hyperbolas, there's many ways to draw it, so I'm just going to pick my way. But basically it looks something like this. It kind of comes in at kind of more of a point. Actually, this should be a little bit straighter. And then it kind of goes in like this. Now notice right away that the parabola and the hyperbola do look kind of similar. But they are different because the parabola is more rounded. It's rounded on the sides more, it's rounded on the bottom more. Whereas the hyperbola is rounded at the bottom, but it's a sharper point. And also, once it kind of flares out, it kind of goes straight. It goes pretty straight pretty fast. And you can kind of see that in the diagrams we have here, in the cutaways here. If we compare the parabola, this shape, to the hyperbola, this shape, you can see this shape is much more rounded. Even at the sides, it's more rounded, whereas the hyperbola kind of goes in a straight line, almost a straight line anyway, once it gets far away from the point, and also the point itself is more pointy, for lack of a better word. It's more of a sharp thing. So a lot of people think hyperbolas and parabolas are really the same shape, but they're not the same shape, and they have different equations as well. So this has no math in it. There is an equation for a circle. We're going to have a whole lesson on the equation of a circle. There is an equation of an ellipse. There's an entire section on figuring out the equation of an ellipse. There are equations for parabolas. We've actually seen them before. We're going to revisit them here as well. And there's an equation that describes these pair of curves that we call a hyperbola. The purpose of this lesson is not to teach you those equations right now. I'm going to teach you those equations in a couple of lessons. The point is to tell you that all of those shapes can come from slicing a cone. And that's actually kind of neat. Because why? Why do we care about this? Why do mathematicians care about this? Well, we obviously know circles are important. I mean, lots of things have circular shapes. Lots of things have elliptical shapes, but what does a parabola really mean in real life? What does a hyperbola really mean in real life? So what I would like to do is give you a concrete example of why circles, ellipses, parabolas, and hyperbolas are all very, very important and very, very useful. And I'm going to give you only one example. There's many, many, many examples. We're going to talk about the orbit of the planets. A low amount of energy is a small ellipse. A little bit higher is called a circle. Higher than that is called a larger ellipse. More and more and more energy gives bigger and bigger, bigger ellipses. Eventually you get to the escape speed, in which case it's not an ellipse at all anymore. It's called a parabola. And beyond that is called a hyperbola when you have escape velocity, when you have velocity greater than the escape velocity. Now, in the subsequent sections, we're going to dive deeper into these conic sections. We're going to talk about what exactly are those shapes? How do we construct them? And then we're going to talk about the equations of circles and parabolas and ellipses and hyperbolas. And we're going to solve problems where we try to write the equation down, figure out what the focus is, figure out what the vertex is, figure out all these different things about these conic sections. And I hope that by learning about orbits and learning about transmitters and receivers and satellite dishes, you can see how important this kind of stuff is to everyday science and technology. So follow me on to the next lesson. We're going to dive a little bit deeper into how we get these exact shapes and talk about the math behind it in conic sections.